Excellent. All right, so we're going to talk a little bit about game theory today, okay, as planned. And while in my initial plan for the course, I thought I would only do one lecture on it. But when I prepared the lecture, I think it's a lot of material. Maybe we'll see how it goes, but maybe we'll do two on them. As of now, I tried to compress a lot of it in this one lecture, and I'll see if I will do one more. Okay. The idea is that there are actually two different aspects of game theory, which are, if you like, pretty similar, pretty related, that are interesting from a reinforcement learning point of view. So we'll try to at least talk a little bit about both of them today. Let's see, where is this? So we'll talk about what I've called Markov games, which is how originally one thinks of game theory, normal form of games. We'll talk about the sequential games. So the question is, maybe I should, rather than going directly to that, talk about good old game theory without any of our learning issues for a minute, right? So, how many of you know anything basic game theory? I've heard of Nash equilibrium. Okay, one hand, I think. Okay, so I will just revise a little bit. Not too hard, but very basic thing. So game theory usually thinks there are people whose actions interact, right? So these people are, in game theory language, are called players. What we have been calling agent. One and same thing. And traditionally, there are two kinds of games. One is called normal form. This is where each of the player, so every player can take an action. This is done simultaneously. Okay? And when everybody has taken an action, depending on all their actions together, each of them get a reward. So depending on all the actions, they get a reward. So the motivation for this is typically comes from industry or manufacturing. So suppose you have two companies, company 2, right? They are competitors, they produce the same thing. So if you produce more, then of course you will probably earn more. But if you produce more and they also produce more, then the price will go down and you will not earn more, right? But you don't know how much your competitor is going to produce. So your action, so your choice how much to produce, by itself, you don't know how much to produce because it also depends on how much they will produce. So you analyze this by coming up with a strategy. You solve such a problem by coming up with a strategy that says what action you should take every time. So the traditional game theory, if you like, there is only one, so at least in this normal form, there is only one state. I will just say this, if you know anything about bandits, which we'll talk about some point of time. So the traditional game theory will correspond in what I will just tell you to something that has only one state. Okay, so this is one kind of game theory, the normal form game theory. And we'll begin with that. But I think for most of the people who want to do a project, you're interested in what's called sequential games, where each player takes a turn to play something, like chess, right? White plays and black plays and white plays and black plays. So those are called where you see what the other player has done before you make your move. So that's a different kind, slightly different if you like. So the other thing is the sequential games. One, which I just said, and this is more or less intuitive. There are slightly different aspects of game theory. But I will not go through this background. We will see the same exact concept. So here there is strategy for first player. There is a strategy for second player. If this player has a fixed strategy, then you can have a best response to that strategy. Suppose this guy is always producing some units of material, some units of output, then you can decide to produce accordingly a certain fixed amount of product, which will make your profit the maximum, right? So that the price is right for the amount you produce and so on. So that will be your strategy. But if this guy changes how much he produces, then this guy will also have to change how much he produces. So for every policy this guy has, there is a policy this guy has to have that matches up, right? And when both of them cannot get a better policy given the other person's policy, it's called Nash equilibrium. But we'll go through this in our setup in a minute. But this is just kind of a vague reminder. There are lots of applications, right from economics, where it emerged actually, like how much to produce given your competitors. We don't know, that's strategic. That's where it emerged. But there are applications to almost anything. You know, in social sciences, they call what's called a social trap, where if every individual pursues their best interest, then it can be two things. It can either be that as a whole, society is getting a sum, everything is getting better, or this can be devastating because their interests are so conflicting that they're cutting throats, essentially. Right? So, depending on the situation, trying to optimize your own personal gain may or may not be of of global interest for the whole society, so to speak. Okay, that said, let's get into our kind of world. So actually, I wanted to do these slides again this morning, but I didn't get the time, so I'm worried if there were typos, but I think I always make typos. So you guys would understand. So we so far had a situation in reinforcement learning where there was an environment and only one agent interacting with the environment. That's the standard situation. But now, suppose there are a lot of agents. So in the language of game theory, a lot of players, all interacting with environment, right? And as a result of each of their actions combined, there is an action. It's like how the world works. Each of us can do something. We have all agency. But the world moves on. The state of the world depends on what everybody does, right? It depends on what Putin does, what the oil company does, what the petrol pump does, how much you pay when you buy your gas for your car, right? So it depends on everybody else how much you pay for your gas price. So there are various agents, and depending on how each of them act, the state of the environment changes, and each person gets a certain reward. And everybody in this thing is supposed to be in some ways rational or selfish or whatever you like to call it. They're trying to optimize their gain. They're trying to optimize their own gain. But you cannot completely optimize because you cannot control other people's policies. So suppose I'm agent 1 and all the other agents have a fixed policy. They are all determined. Then I can consider all of them as part of the environment. Right? I can consider all of them as part of an environment. And what will that be again? It will look like a good old MDP. Right? So how do we kind of mathematically formulate this situation? So it's called a Markov game. So again, it's like an MDP. It's a generalization of what an MDP is. So you have an environment with states, just like an MDP. But rather than one person performing actions, there is a set of n. We have n agents performing actions. And both the transition in the environment does not depend only on the state and one action now. It depends on state, action of person 1, action of person 2, action of person 3. So it's a function from state times all these action sets into the states. So this is how the transition will happen. Okay, and the reward will also depend on all individual actions together. So this is one level more complicated, if you like. Okay, so this is, but here you're also assuming that all, so this is, as I was saying, there are two kinds of games, sequential games and normal games. So this is kind of a generalization of the normal game. So a normal game in this setup would be where there is only one state, the traditional good old normal form of game. In this language would be just one thing. But more or less everything from here can be stolen and applied. So we will do that. Okay. I think the idea of what the value function should be for each player is kind of obvious. You take the expected sum of rewards in the future, discounted by whatever factor of discounting you want. That's more or less the obvious choice for each one of them. But it's not possible to just directly optimize, find a policy to optimize your. So when you had an MDP, there was a deterministic policy that you could use to optimize your strategy to your games. But when you have multiple agents, you cannot have that. So for example, a good example, a very simple example, and obviously the most canonically used example is the game of rock, paper, and scissors. Right? I don't know. I'm sure everybody's played that as a kid. So if you have a constant strategy, if you are always having a rock, then the answer to the best response to that strategy is always to be pick, right? But if the other person is constantly changing their strategy, you are also forced to constantly change your strategy, right? So the best strategy in some ways is trying 1/3 times rock and 1/3 times paper and 1/3 times scissors, right? Randomly. That's the best strategy. And such, if both the players do that, that will be what would be a Nash equilibrium. If any one of them deviates from that, the other person will start winning. Right? So this is the idea that it depends. The policy that one person has is no longer a deterministic optimal policy. you will have to have a probabilistic optimal policy. Even this most simple game that even children understand that doing always the same thing is not going to win that. Right? So it is obvious that you need a non-deterministic, a stochastic policy in this situation. Okay, so I kind of don't said I was going to change things today, but okay. So now we can formalize. Like first thing we did with MDP is we had to formalize what our objective is, what our goal is, right? And what we said our goal in MDP was to find a policy that optimizes your return. But now to formulate this, you need not just your policy, but the policy of all players, all agents involved. I think I start mixing up the words somewhere. So just so to be sure, I don't know what's written on the slide. Player equals agent. Strategy. This is good old game theoretic word for policy. And what we call reward in game theory is called a payoff. Okay, so these are the alternative words for the same thing. The game theory literature will use these three words. And maybe maybe I don't remember if I've knowingly or unknowingly interchanged them. So if you see that, you know what I mean. Okay. So again, so what you start with is a policy profile. So everybody, so you get the first agent has policy pi1, the second agent has policy pi2, and so on. So that's, if you assign a policy to everyone, that's a policy profile. Okay? And if you fix, so there is a notation here, I think it's called pi minus I. It means the policy of everybody other than the person I, agent I. So pi minus I is the other people's policy other than the I guy. Okay? And if you fix the pi minus I, so if you fix all the other agents, right, then the job for the first person will be to find the best response to all of the other ones. But in this case, as I previously mentioned, you can consider all the other ones as part of the environment because their policy is now fixed. So you can just consider that to be a stochastic environment. And now you could use all the things that we learned before. All the RL method, all the dynamic programming methods will be directly applicable to find the best response against a fixed set of policies for the other agents. Okay? So this is where you could pretty much, if you know all the other agents, you could already solve it with the knowledge you have acquired so far. Any questions? So what can happen? That's Nash equilibrium one, right? I suppose. So technically, a Nash equilibrium is defined when each of the players has a policy, so that if I fix all of the other ones, my policy is the best policy. There is no point for me to change my policy. Any other policy cannot be better than what I currently have. So my response is currently the best response. So it gives me no incentive to change my policy because any change I will make, I will lose. Right? Similarly, this should happen for all the agents in the set. So all the n agents should not feel any desire to change their policy because if they change, the current policy is the best response to what everybody else is doing. So when this happens, nobody would want to change their policy. Everybody would play the same game. And that situation is called Nash equilibrium. Okay? The funny thing about Nash equilibrium is this theorem, and so maybe if you have one more class, I will talk more about the proof of this theorem, for example. The theorem says there is, in finite situation, there is always a Nash equilibrium. There is always one. Okay? And one way to heuristically see this is as long as I cannot, if I find a policy that's best response to you, and then you find a policy that's best response to mine, we keep doing these things, they have to some point of time converge. I keep changing my policy to be best response to what you change to. At some point of time, this cannot go any further. Okay? And this will come into a deadlock, and that deadlock is Nash equilibrium. So this theorem is essentially saying, in a finite situation, you will have no other choice but to hit a deadlock as you change your policies to beat the other person. Okay? So I don't know if I'm going to say more about this, but this is the practical application part of reinforcement learning. The multi-agent, it's used in robotics, so multiple robots, multiple things doing things together, or in other places. Also more game theoretic analysis. Okay. So now I'm going to change gears. So if you have another lecture, I'll come back to this. But now I'm going to come to something simpler and talk about this other kind of games, the sequential games. Right? And again, this idea of Nash equilibrium kind of makes sense here. We'll talk about it in a second in the sequential game setup as well. But for most purposes, consider games which are zero-sum games. So I have to admit one thing about the rest of the lecture. I had planned something different along the same lines, but slightly different. But I watched last weekend a lecture by David Silver on the same topic. It's on YouTube. It's very nice. It's pretty long, but it has influenced me a lot. So this presentation has been very influenced by it. This was not the original plan. How was I going to do this? But it's an improvement, I would say, in my opinion. So, but I would tell you the source where it comes from. So it's been influenced by David Silvers, who has worked on these things. So of course, one has to take other people's expertise, borrow them. So the zero-sum games are actually the first things that were introduced in game theory. But not all games are zero-sum games, right? So if you know something like The Prisoner's Dilemma, it's not a zero-sum game. A zero-sum game means if one loses, the other wins. If one other loses, the first one wins. But there cannot be something like a draw. Or something in between, right? One person's gain is other person's loss. So in all the games that we practically think about, where there is a win and a loss involved, like chess or whatever, they're all, or rock, paper, scissors for that matter, they're all zero-sum games. If there is a win and a loss situation, you can always think of it as a zero-sum game. And now we are going into a sequential setup. Did I write it? This is all about now sequential. Okay. So anyway, so the point is that this is sequential, and for sequential games, there is usually what one calls a game tree. How many people are familiar with? When I say the game tree, it's obviously clear, right? You don't have to be familiar. It's clear to you what I mean. But I will draw a picture. So let me just. Is something today here, or am I just getting so dry in my speech I cannot? My mouth is getting dry every minute. Okay, so in a sequential game, so you have two players. So traditionally, like in chess, first player is white and second player is black. Okay. Now you start with some state, which is the chessboard position. So maybe this is your initial chessboard position. And so you have pieces right at the back and right at the back. This is your first state, and the first guy has some choices of moves. Right. So every choice of move the first person makes, you get into new states. Now I should have used the access to so much color choice. So I will do that. This one. Okay. So these are all the actions of the first guy, A1, A2. And now the opponent starts making moves. So depending on whether this guy had made A1, the opponent will make a set of moves. And you'll end up in new positions. Okay? So this is what a game tree is. So game tree is a tree as the game progresses, your states progress, and you get a tree of states connected by actions. So all possible actions and all possible states. So this is traditionally what's called a game tree. Okay? But at the end of this, there will be some terminal state. There will be a terminal state, so deep down there. There will be a terminal state in which, if I draw it like this, which means that white has made the last move, and it's a terminal state, that means black has won. White has won. And if I go down and get something like that, I'll get a -1. Right? So +1 will mean, so for example, in a game like chess, but it doesn't have to be like that. You can have other kind of games. But let's just consider for sake of concreteness, something like chess or checkers or something like that, where the winning is +1 and losing is -1. Okay? So now if you come to the state, right? If I am on the level where I could have come to this, the +1, what should the guy who's going to achieve the score here will do? You necessarily would like to go to this state rather than any other alternative ones. Right? So this thing should have a higher value than all the other alternative states. So what you can do is assign these terminal states the value like +1 or -1. You can assign all these terminal winning or losing states their values. And if you assign the winning and losing state their values, at the step before, you know who is winning or losing. What's your best chance of winning or losing? So that can be assigned a value. So how do you do that? how do you assign values all the way up? It's an algorithm called the minimax algorithm. Is the most obvious thing that you would do if you want to build values from down to up. Okay? And how do you do that? So are you familiar? How many people are familiar with the minimax algorithm before I spend 5 minutes explaining it? No, no one. Okay, good. So this is just, it's, I mean, a realistic game, I can never draw pictures. So one has to make some sort of an example tree. So suppose you have a tree, but this is your root, and then you have some red and some white, and then some red. This is just example. I don't want to draw every layer. So what you want, so suppose at this level, at the lowest level, I know the scores. So here some score is +5, -3, 2, and 7, and +9, -7. I don't really care so much, right? So if you are the guy making this move, the black guy, which one of these two you would choose? You choose the smaller one. So at this level, you will always choose the minimum, right? So you take, at this situation, you take -3. So you assign this node. If you know these terminal values, you assign this guy the value of the minimum of the thing from the children nodes. Okay? So when it's black's turn, you assign this thing the minimum of the children it has. So now I don't know what numbers I wrote. I don't know. 3 is it? But I don't remember. Some number it was 5. Let's just say. Right? But if you're a white moving, and you have these two choices, which one of them you will take? You will take the bigger one. So whenever you have the white action, you take the maximum. Whenever you have the black action, you take the minimum. So here, if this was -3 and 5, this guy should be scored as 5. Right? So if you know all the bottommost, all the leaf values, you can propagate the values upwards. Every time when you are moving for the black, you take the minimum. Every time you're moving for black, you take the maximum of all the children. And this way you can give value to all the states, starting only from the value of the leaf states. Do you see what I'm saying? More or less what is the right choice, right? So this is what the minimax does in any game tree. So the game tree, let me maybe write down. So minimax assigns values to nodes in a game tree. tree, given values for the leaf nodes. And this is done by one taking the maximum of all children nodes when white has to play, and take minimum of all children nodes on black. Okay, so that is why the name. Okay, so it propagates upwards, backwards. This is a back propagation, if you like to call it that. Right? So this way you could know values for your whole tree, essentially. Any questions? Because this is something I will use all the way today, and if you have another lecture, we'll use this quite many times. So I don't know if this thing is recording because I have no idea, but I hope it is. Okay, so in order to do anything, you have to do you have to assign a value to a state, and the expected value of return of being in that state is what you're interested in. And this minimax algorithm is one way, if you could go through the whole tree, is one way of computing the actual value function of a state. This is the whole point. And I'm sort of making this picture very precise because I'm kind of treating this as deterministic, but there might be other factors. So let's not talk about it for that now. We're going to be deterministic, at least in this lecture. Not the policy. The policies will be not deterministic. The policies will be stochastic. Like in game of chess, a game of rock, paper, scissors, your policy is stochastic. Right? But your action, you can only take one action. Sorry, what am I saying? Your tree, like what moves, when I make a move where I land, is not like in backgammon. It doesn't depend on throwing a die. If I'm only considering games like chess, where a move has a deterministic change of state. You see what I'm saying? Your policy need not be deterministic, although your game is deterministic. Each move has a deterministic consequence. Whereas in some games, like in backgammon, each move does not have a deterministic consequence, or some other game of chances. Okay, so so you could now consider a policy if you have this tree figured out. Suppose you have this tree figured out. It is only possible to figure it out in very small games. In any non-trivial game, you'll never figure this tree out. It will be solving the game completely. But it's just so big, this tree is so big that you cannot figure it out. But let's say you could figure the tree out. It gives you obviously a strategy as black or white, what to do next. Because you'll always move, if you know the value of all the children nodes, you will always move to the one that is the biggest value. Right? So that will be your policy. The minimax gives you that gives you a policy that we'll call the minimax policy. If you have this tree, you have a policy which is the minimax policy, which is go to the child, take the action, and go to the state which has the maximum value. Okay. Obviously, it means if all the chess positions have some rating, what move should I make? I should make the move where I will be in a position with the highest rating amongst all the chess positions I can go to. So nothing special about it. The minimax function, the minimax value function, as you will obtain using the minimax, is unique just because how we have built it from this tree. There is no choice. How we build this using the tree, there is no choice. So you get a unique function. And because of this choice of policies, if both players follow the minimax, they will be in Nash equilibrium. So Nash equilibrium in sequential games means that given the history, you're sitting at a situation that's your best choice of moving from that situation. Right? That is what it means in sequential games. And so you have ascertained a kind of a theorem that there will be a Nash equilibrium, which is our goal to find in all these games. Okay, so this is kind of the only theoretical bit for today. We'll discuss this next time. So in theory, okay. I mean, in theory, if you could find this whole game tree, you have solved the problem. But in practice, is there an issue? It is fine, but in practice, as you go through the depth of the tree branches exponentially big. And for most games, it's just unbelievably big. It's impractical to deal with the whole tree. So although this is a good theoretical picture, and we will use this picture in understanding things further, it does not help you solve the real problem. Okay? So what do you do in reality? So now that we have an understanding of it theoretically, what do you do in reality? So before I go to reality is messier than theory, always, as a rule. Everybody happy with what's happening in theory? I take your silence to mean all is well. Okay. So in reality, what you do is you don't know the exact value of the function along its tree, along this kind of a game tree such, and you cannot go to infinite depth. So what you can do is you go to finite depth and take a heuristic value at the end of finite depth. Right? So in chess, we spoke last time as well about this when we considered linear feature vectors, and I will do that again today. Where did I put it? It's just very dry today, or I'm getting so thirsty. I finished a bottle of water. I'm still thirsty. Okay, let's just get this off for a second. I'll come back to it. So what you do in reality is you are in a current state in a game. You have current chess positions, right? Whatever things are happening here. You consider all possible actions to the next positions and consider all possible your opponent's action. So when I go to the opponent, I change colors to the next position and so on. So up to a certain level, as anybody plays, as anybody who has played any game like that, you consider your all actions, then you consider, if I have done this, what can my opponent do? Right? And if my opponent has done this, what can I then do? And then you say, aha, if I do this, the opponent does this, I will do this, and I will be at a better position. Right? This is how you play chess, I suppose, or any other game of strategies played like that. You go a few steps down, and you think to yourself, at least, maybe later on turns out to be the wrong idea, but you think to yourself that if I've gone 3 steps down here, that position looks much better for me, so I'm going to go in this direction. Okay? What happens is often you are mistaken. If you are mistaken or your opponent is much smarter, they go in some other direction where your position is not good. But let's not go into the human version of it. Let's go into the computer version of it, where you calculate this to a certain depth, and to all these leaves that you have now have. So this is only the game tree up to a certain depth. The game tree up to a manageable depth. So you start with the game tree at your current position up to a manageable depth, and you assign a heuristic value function to the leaf nodes. So all these leaf nodes, the leaf states, positions, whatever you call it. Okay, so you assign a heuristic value position to this, and then you propagate it backwards. So take here the best, for whenever you have black moving, take the minimum. Whenever you have white moving, take the maximum of all the children. Alternatively, take minimum and maximum of all the children. So back propagate using minimax. And this gives you one algorithm to assess your current choices. So if you're here and you have these choices to make, when you start with some heuristic values, some depth down, you will know what should be the back-propagated values for all of your children, and you will pick the one that has the highest value. Right? So this is the policy that this kind of very simple thing where you assign a heuristic function gives you. What is the problem with this, and what should be done about it? Why should it, if this was like this, why do we even talk about it in a reinforcement learning course? What is the problem with this approach?
How good you can heuristic value?
Yeah, how could you come up with the heuristic value? How stable it is? So the thing to learn are two things. One thing is to learn here. So this heuristic value function, in traditional approaches to solving or playing games, this heuristic value function is provided by experts. So I suppose all of you have heard of Deep Blue, right? So Deep Blue had a heuristic value function. If I remember correctly, people say something like it had 8,000 features, depending on 8,000 features or something like that. But these features were designed by expert grandmasters. So each position had to be evaluated using some lot of features designed by expert grandmasters. That gave them a heuristic function. And using that heuristic function, they did this kind of a minimax search. But in fact, they did a much deeper minimax search. They had this parallel computers and some alpha beta searching techniques and all that. They did a very deep minimax search. And they could beat Well, they could beat Gary Kasparov. I mean, that's no trivial feat, right? So this does work, but as you point out, and you pointed correctly, the problem is how does one get a heuristic function? That is one of the two problems. The second problem is, of course, how to manage the search step. How to manage the search. And can one do both these things together? So these are the kind of problems that you have. So the problem so this is the right approach, but the problem is how to learn a heuristic value function. That's one thing, and second problem is of course related managing search. Okay. So I suppose I said everything that's already in the slide, but let's just be sure. I don't, as I said, I didn't look at them. Yeah, so this is basically what I've said. What you do is what's but maybe it's good to see this slide. So what you do is what's written on the slide. You give the leaf nodes some heuristic values, propagate upwards to your current by using minimax, alternatively assigning the minimum or the maximum, and you try to choose a policy depending on that, and then that's what it is. The thing is, now we're going to talk about learning this value function. Okay? How can we learn this heuristic value function so that we can use our RL techniques to learn this heuristic value function? Right? And these will be just standard RL techniques, TDs, TD lambdas, Monte Carlo. Nothing very different from what we have done so far. Okay, but sometimes cleverly done. Okay, so I just want to be sure I have not missed anything because I haven't looked at these slides today. Okay, so one way of solving the problem is where I'm going to start this is by assigning some sort of feature vector to your. This is also what basically Deep Blue does, right? So they take 8,000 hand-picked features, but they also assign these features weights, which are given by some experts, right? So you can also take features. Nobody stops you, say, from deciding what features are important in your game. That you can also decide. But how to say which feature is more important than which other feature? That would be one thing, one way of learning. The thing is that, let's just learn which feature is more important than which other feature. That could be a way of doing things. Okay? But you could take the state space embedded in, get a feature representation of it, and consider a value function as we did in the last lecture, taking the inner product of the feature representation with your parameter W. So now this can be, for now I'm saying this representation, but you could take any other. That's fine. Okay. Okay. So yeah. So I tried to. This is again inspired from what David Silver's presents, and I tried to put it in here, but it doesn't look as good as this. But of course, these guys made AlphaZero, so they know better, right? So, see, what they claim or what they suggest is you can start with a vector that says its features are whether a particular piece is in there or not. So if a rook is in there, you put 1, If a rook is not there, you put 0. If a pawn is there, a particular pawn is there, you put 1. If the pawn is not there, you put 0. So take a binary feature vector for all the pieces. Take a binary features. Also, you can take features like where the pawns are, for example. Combination of things, right? And then assign to each of these, there are some traditional values you can assign. And so this gives you some sort of a starting value function for your game. Okay, so this is the starting heuristic value function, and it is actually very important to have a good initial value function for the heuristic thing, so that your program actually learns and does not diverge. So in these situations, often there are no theoretical guarantees of things converging, and only when you pick the right art, things seem to converge correctly and very nicely. So there is, in this business, not just science to it, there is also some art to it. I would not underemphasize that. So this is one particular way of starting with the feature vector. And now, so the other thing that probably all of you have heard is, you think? No. Yes, I'll just keep talking as long as I can. My mouth is really dry. There is still a second. Okay, so this is describing how you actually do the learning. So probably all of you have heard that how they train their programs in all these fancy situations, at least, is by self-play. And what you do in self-play is you start with a function approximation to your desired value function. And you have to note that if your game is deterministic, just having the value function is sufficient. Right? If the game is deterministic, then, as I had already said a few times, if you are in a state, what move you make the move to the next state which has the highest value among all the children. All the positions you can go to, you take the move which has the highest one. So traditionally one calls it the successor position after an action in a game language. So you go to the successor which has the highest value. So if you know the value function, you have a policy. You know the value function, you have a policy. So it's good enough to just, in deterministic games, it's good enough to just describe a value function that suffices. All right. And now once you have picked a value function, depending on your parameter, and kind of obtained, then each step, in each action, you try to choose an action which either minimizes in case of black or maximizes in case of white. The first player and the second player in our order of moves. And this produces, a recursion, sort of a TD kind of way, what you have to do next, right? And this will optimize both the joint policies of both the players automatically. So this is the whole point of repeatedly playing and letting the computer learn using taking actions and maximizing from what they know. Okay? So you maximize from what you know. So currently you have a value function, you play a game, and depending on the result, you have a new value function. You play a game again, The value function keeps getting updated and updated and updated for both white and black. And eventually, it should give you optimal policy. So there is no theoretical guarantee of this working, by the way. So I cannot give you proof. But this seems to be working in all practical situations. So this is what is mathematically interesting for people who want to do math, is to find real conditions when actually such things will converge and when they will not converge. Maybe I'll talk about some of that next time, or if you have another lecture on games. Okay, so now comes the nitty-gritty. So far, it's all well and good, it's all theory. How do you do things in real life? If you have a game to solve, which is what some of you are planning, you will have to learn some kind of a value function. You could do also a policy kind of iteration here, but since we haven't got policy-based methods, we'll just stick to that. So you have, and apparently all these things, AlphaGo and AlphaZero, they're all based on value. They're not, the best known examples are based on the value functions. Okay, so how do you learn the value function? Right? So one thing is the simple TD. And the simple TD does the following. You get some experience, make a new move, kind of understand how your thing is, how the value at the new position is, whatever heuristic formula you have, and you try to update your value using your standard update formula, which I haven't written. Do you remember how you update in TD? Alpha times the difference and the gradient. So there is some cost function which you can define, and there is this difference, and you have moved this here. So whenever I write an arrow like update, it means a TD update or a TD lambda update or something like that. Okay? So you learn a value function using a TD update by going through moves after moves after moves. Yes, you learn a value function. That is what the TD does. By actually experimenting, by actually getting experience, you learn a value function. You update using a TD rule. And once you have done that, you take a search tree up to a certain depth and try to back propagate the value. So there is no learning in this second step. In the second step, you're only back propagating value in the search tree. So this V plus is just a minimax algorithm result from a certain depth. So first you find the heuristic. As I said, the problem is what is the heuristic value, right? That is what the problem was, as you pointed out. The problem is what is find the heuristic value function. So you find the heuristic value function by assigning the next state's value to the current state by some up to a certain error, right? As you experience things, and then apply this minimax algorithm. So if you go up in this thing and you get a new value function from which you will make your policy. So policy will be made from V plus. Okay. So is this kind of clear, or shall I? Because I think I haven't completely written the next slide, but I'm going to explain it anyways. The next couple of topics on the board. But the thing is, this has to be crucially clear for understanding the variance. So maybe I will explain this on the board again. Is everybody fine with this? Oh, now how can you complain? Or can you? Maybe you have notes. I hope it's not something wrong with me. Not getting sick or something, but I'm so. So my voice is still audible, right? You guys can still hear and understand what I'm saying. I hope. And I'm still okay. So maybe I'll explain this simple TD version first before going into more complicated versions, which unfortunately I don't think that the slides actually only mention their name and not their content. One of which is fairly complicated. Okay. So the simple, is the wrong color? So what it does is you are in a position and you have, so first you have chosen some sort of a value function approximation. Okay, so is approximately what you currently consider your V star, which we defined using using the minimax principle before, right? So we already know what should V star be in ideal situation. You have your current approximation of it. Okay? You have your current approximation of it. And suppose you are in the state ST. So it looks like your current position, you have some king and some queens, whatever, and you do something, you move on, you take an action, you get to a new state. So this has some value, value STW, and this has a value, sorry, ST plus 1 W. Okay, and what you do is you update this towards update this value towards this value, because what you know is that if you would have happened to make this move down the line, this is where the effect is coming from. And maybe you could take another experience, maybe go in another direction and see what that happens to be and update the value according to that. So the update happens by the TD rule. So VSTW is updated by TD rule. So TD rule means alpha times the difference times I'm going to kind of fuzz this away, what that means. So something like that is your updated value. Or there should be an alpha here, right? Okay, so you move this value by this TD rule. And you keep on collecting experiences and trying to get more and more values. Right? So start with something and you keep collecting updated and you get a lot of values. Once you think you have learned the heuristic function, so after sufficient experience, the V as W is your now heuristic function, value function. Okay, it's now your heuristic value function. And now you could apply what I said before. So you could assign all the leaf nodes in certain depth of gain tree search this value and consider the minimax algorithm to find the best action at a given state. Okay, so this is the heuristic system, and now apply minimax to obtain what at least some people write. So in this step there is no learning, only this step there is learning. Okay, you see that? And this is the simple example of TD learning. So the thing is that do you think this is going to be very efficient? Although it has had produced result actually. I forgot, I'm no expert on this subject actually, but it produces some very nice results. But what it tells me here is there is an obvious reason to think there should be something better than that. What could be better than that? Any idea? Okay, let's. Yeah?
What I'm using to make everything.
Yeah, but how should we improve? So right now we are doing something where we are not using learning and your minimax search at the same time. We're doing them separately, right? But what one can do is the following. So there are two versions of it. And one version is rather easy to understand. The second version is also easy to understand. It's not easy to explain. Once you understand it, it's easy. It's harder to explain it to anybody else. So I think the one version is called TD root. Again, the wrong stroke. Okay, and it goes like this. So you're currently in this state. So this is, maybe I'll need one more color. Okay, I'm sure this is different case for you guys. Let's see. So this is your current state. So you're interested in this state, and you go down and you get somewhere here, and you go down again. So what you realize about the minimax thing, so if I say go down the tree 2 steps down, and I use the minimax to update the thing on the top, there is usually one value, one leaf that you will use to update the top, right? You understand what I'm saying? So amongst all these, so whatever values there is, A, B, C, D, you take here the min, you take here the max, min again, and here you take the max. One of these values will all of the time, all the way go up here. So let's just say it's this one. So this is what is creating the value here. Okay. So in minimax algorithm, you always know that one of these will create the value there. Okay. And now what you do is you in your current valuation, so there is a current valuation. So current valuation says take this action. The current valuation says go here. Chosen action. Chosen move. Okay. So what you do in the TD root thing is you go to the chosen move and you do a tree search at the chosen move. So this is now that guy. Okay, and you do a tree search here. I'm not being colorly accurate, but you know what I'm trying to do. I'm doing a search here with the current values, and one of these values is now by Minimax trying to change this guy. Okay, so this is my experience from the current situation. I take, say, the best move, for example. I make the best move because of my current values, and from the current values, I look at the tree and go down there. And now what can happen is, like, this might be, so this is a wide. Okay, so this is 5 and this is 10. So of course you want to go towards 10. Okay, but when I go to the 10 guy and I go a few steps down, apparently what happens is that there is a -2 here, and it is trying to become that. After 2 moves down, it looks like this thing is not 10, but this thing is -2. So this thing is influencing this, or it could be +5 or whatever, right? So 2 steps down, it feels like this number is not 10, it's some other number. Could be bigger, could be smaller. Right? So what you should do is not just update your thing to that, you should update this number using a TD to here. You try to change the value here from the value here. Because this means if I had followed the burst move and gone down the drain, I would be hitting here, and this is how good my actual estimation should be. So this is called TD. It seems to work, but the heuristic is, of course, if I'm going in this direction and then going down, eventually after a bit, I would know whether I've been in a better world or a worse world. And accordingly, I should give myself a knock up or a knock down from where I am. So this is combining two things. And there are so many combinations of such kind that it's hard to keep track of. You can produce your own. People experiment with this all the time. Okay. Oh, are we out of time? We have time. Oh, we have time. Good. Then we can go through one more of them. All right. So is this complicated? Or at least you can say no. No? Or yes? A little bit. So why is this so interesting? I mean, so sequential games are usually just games. I don't know many problems which are modeled purely on sequential games, many real problems. But still, if you can solve sequential games, it tells you something about, the robustness of your engineering idea, right? What is more interesting from real world application are the normal games, because this is what happens all the time. Everybody is trying to do something at the same time in the world, and the net result is depending on all the people doing whatever they do. Okay, so I'm going to talk about the other version of this, which is called the TD leaf. Okay. And that is that is somewhat, to me, this one was more clear than that one, but I realized that they are pretty similar ideas. So you start with the current state, and you're going, suppose, in this direction. And basically, you're going in this direction because of this guy. Okay? So I'm going in this direction because of this guy. So what I do is I go here and I start doing a new search tree down from here. I am drawing very early diagrams, but drawing is certainly not my greatest deed. So now you realize that this value is most affected a few steps down by this leaf. Okay. So what should you change? So in TD root, you use this to upgrade your value of the root. And in TD leaf, you use this to upgrade the value of the guy that was contributing it to you to go this direction. So it affects essentially in the long run whether this direction will be a viable direction or not. Is this a good direction or not? Because you have gone one step down in your search tree, or whatever number of steps down in your search tree, it is going to influence whether the direction you have gone down in the search tree is a good direction or a bad direction. Okay? And if you understand my, I think, yeah, it is what it is basically. I don't know of a better way of explaining. This is more or less what happens. Okay? So each of these, as I had already advertised that lecture by David Silvers, each of these there are game programs based on all of these three TD algorithms, and successful ones and how successful they are is also well understood. So this is one approach to it. Whereas what I was originally thinking about talking today is more in the direction of what's called the Monte Carlo tree search. But now that you have covered the basic of it, I think you can more or less, if you are interested, you can look it up yourself. There is an issue with Monte Carlo. For everybody who wants to implement it, there is serious issues. But when it works really, really well. So that is what I understand better. That is what I wanted to talk about. But well, it's also fun to learn something new and talk about it. So, maybe we'll have one more. I will see how the time is available for the lecture. We'll have one more of class for game theory related issues. But this is, I think, a good startup. Okay, so maybe I'm going to stop here. Yeah, we are anyhow going to run out of time to say anything more. All right, so